Good afternoon. Welcome to 0 Days and Mitigations, Roadways to Exploit and Secure Connected BMW Cars in South Seas ABE with Zhiqiang, Michael Gruffke, Hendrik Schweppe, and Wenkai Zhang. Before we begin, a few brief notes. Stop by the Business Hall located in Mandalay Bay, Oceanside, and Shoreline Ballrooms on level 2. The Black Hat Arsenal is also in the Business Hall on level 2. Lunch will be in Bayside AB from 1 to 2:30. And don't forget the merchandise store on level 2 and the session recordings from Source of Knowledge. They have a desk on every level. And also thank you for putting your phone on vibrate. It makes it easier for the rest of us to ignore the ringing while we wait for your voicemail to pick it up. Our speakers.
Let's start today's topic. And today's topic's name is 0 Day and Mitigations, Roadways to Exploit and Secure Connected BMW Cars. I think today's topic will be a little bit special because we have two groups of persons. The first person is from KeenLab. We are focused on how to find the weakness of the car. And also another part from BMW Group, and they are the experts to how to secure their car. So two kinds of things, and we get together to talk about how to secure a car. First of all, what about us? We are the researcher from me and Zhiqiang come from Tencent King Security Lab, and we are focused on the research of connected car. We have the 2 years Tesla research, and you must know that. And also this year we'll give the BMW research. First of all, let's talk about some of the timeline. We started the research at 2017. It almost took us almost a whole year to do the research because one of the difficult to do the research of BMW car is you had to reverse a lot of things. You had to understand the complex architecture of the car. So it spent almost 1 year. And then at last year, we report the problem to BMW Group, and we get help with each other. We try to talk about how to fix the problem and the details of everything. And finally, at the August of last year, finally we can let everything get finished. That's the agenda. Before start the technical topic, and I want to ask a question that I really love to ask. And how many guys have BMW cars here? Wow, not too many, not all of you, right? So it seems BMW has a potential market in USA, right? So let's talk about first of all, let's talk about the vehicle components and the exploitation. And I will give you a brief introduction of how the architecture of the BMW car. First of all, the head unit. Head unit is a very important part in our exploitation because we start the research of the car. We just start from the head unit. It's an infotainment system. And then we expand our research to the other components. And in BMW's cars, they call it MBT, head unit. And it's responsible for a lot of media things. And then the TCB, it's we call it a T-box. It's a telematic unit of the car. And it can do, it integrate eSIM in the TCB, and it can go online. It supply the online services to the both head unit and also the TCB itself. And also, it has some telematics function we will talk about later. Then another important component is about the central gateway. The central gateway can almost responsible for such things. First of all, it's about the OBD diagnostic, and then for the to route the CAN message and the flex-ray messages to do the message transport. And also, it gives there's a switch on the central gateway, the OBD use Ethernet, and also the head unit use Ethernet. So you can diagnostic the head unit through the OBD side. Then in our research, we almost try to analyze almost every attack surfaces in the car. For example, the remote attack surfaces is from the TCB through the backend. There's cellular data. And also short message, we analyze this attack surface. And also in the nearby attack surfaces, we have the USB, Bluetooth, and also when you can touch the car, we also analyze this important attack surfaces, OBD2. Then let's talk about something of the whole architecture of the car. As you can see, the head unit and the telematic box TCB, they are on the KCAM4. It's we call it infotainment domain. And you can use the OBD through the Ethernet switch to the head unit. And also the central gateway is responsible for the other kinds of ECU, for example, like body cam, PT cam, chassis cam. And there's a lot of ECU on that. So in this picture, you can see if you can compromise the head unit or the TCB, it's not very, most of the time, you cannot influence the whole car because there's some domain isolation based on the CAN bus and also the Ethernet. First of all, it's about the local exploration. We can start the attack through the USB or the OBD. And then we can plant our backdoor to the head unit. And the head unit can send, we let the head unit send CAN messages, any CAN messages to the central gateway. And finally, the central gateway help us to influence the other ECUs by the UDS messages. And then it's about the remote exploration. The remote exploration is the last parts are the same like the local exploration, but now we can start the attack through the fake base station. And we find some vulnerabilities to plant our backdoor to the TCB. And we use the same thing to influence the other ECUs. And then the talk about how to route the head unit, and Zhiqiang will give you the talk.
Okay, in this part, I will introduce local and remote ways to route NBT head unit by utilizing the vulnerabilities we found in some vehicle services. Basically, NBT head unit is comprised of two systems. The upper layer system is HAO Intel. It's mainly used to handle multimedia functions and provide online service via telematic communication box, which is also known as T-box. And the low layer is HAO Jacinto system. It's mainly responsible for CAN bus communication with the central gateway. And between HAO Intel and HAO Jacinto systems, they use the QNet for IPC communication. And after we reverse engineering the firmwares, we identified some vehicle services which are running in the HAO Intel system, and like diagnosis service, navigation update service, and the BMW connected drive service. And these services can interact with the outside via some common interfaces, including USB port, OBD port, and 3G network. In next slides, I will analyze the vulnerabilities in these services case by case and introduce how to control HAO Jacinto system to send the CAN messages onto the KCAN bus. When we started to research NBT head unit, the first question is how to access the internal network. Because for NBT head unit, the Wi-Fi interface is disabled, but we found a USB config file in the HAO Intel system. This config file can enable USB Ethernet interface and set up an Ethernet network in the system. So if you plug in a specific USB to Ethernet adapter, like a D-Link USB dongle, the HAO Intel system will be assigned a static IP address. Then you can connect to the internal network of the system. And then we try to scan the TCP and UDP ports. And the scanning result shows that the HU Intel system has no firewall filtering rules applied on the USB Ethernet interface, and leading to many internal services are exposed. And these exposed services are new attack entries to the system. For instance, a diagnosis service is running on TCP port 6801. And actually, this diagnosis service running in the HU Intel system is used to diagnose and reconfigure NBT head unit. And there's a dedicated BMW diagnostic tool for the communication with this service, which is called toolset. And the service internally implements a custom UDS protocol. The communication data between the service and the diagnostic tool is also based on a customized protocol packet. And with regard to the protocol packet, it's comprised the packet header and the packet body. The orange area in the header indicates the packet body size, and the green area in packet body is the source ECU address, and the blue area is the destination ECU address. And for standard UDS payload, it's saved in the red area in the packet body. And after some reverse engineering work, we found there's an interesting UDS diagnostic job, which would receive batch script from the diagnostic tool and then write the batch script into the HU Intel file system. And the job then will execute the batch script for NPT head unit reconfiguration. But in fact, the batch script is signed by a private key. Before executing the batch script, the collector signature data should be sent to the service for digital verification. So if you cannot get a private key, it's impossible to achieve the service into executing some modified batch script. But this diagnosis service is multi-threading. When two concurrent threads are accessing the same batch script at the same moment, there's no thread safe protections like a thread lock, so it leads to a classic talk to risk condition vulnerability. And in order to exploit such a vulnerability, we need to create two concurrent threads for communicating with this service. One is DAG thread, it sends the normal request, and another is raise thread, it sends the malicious request. When the DAG thread is verifying the batch script in memory with correct signature, the raise thread is always trying to rewrite the batch script in file system. But the DAG thread is always thinking the batch script in file system is never be modified during verification. After successful verification, the DAG thread would execute the batch script, but the batch script has been modified by raise thread. So by this way, we were able to execute arbitrary batch commands in the HU Intel system with root privileges. And there are two ways to deliver the exploit. Simply, we can exploit this service through a USB to Ethernet adapter. Besides, on a BMW car, an OBD Ethernet cable can also set up an Ethernet connection to the HU Intel system. So this exploit can also be delivered to the service through Ethernet over OBD port. And after we got to load shell from HU Intel system, from this picture we can see that HU Intel and the HU Jacinto system are in a same queue networking. And the next vulnerability was in the navigation map update service. This service continuously monitors USB ports on NBT head unit. And if a USB stick is plugged in, the service would try to search and analyze an updated config file from USB stick, which is called manage_upd.nzdf. This updated config file keeps the information about the compressed map files for navigation update. When navigation update started, the service would try to decompress map files from USB stick into the HU Intel system. And before navigation update service decompresses a map file from USB stick, it needs to pass the updated config file and extract a map file name for decompression. And from the right code snippet, we can see that the service uses sprintf function to construct an absolute file path with a map file name. And this map file name is retrieved from the updated config file. And the worst thing is there's no bound check on the file name buffer, which is allocated on the stack. So if the map file name in the updated config file could be modified with more than 1024 bytes, the file name stack buffer would be overflowed. And in fact, this updated config file is not digitally signed, so we can directly modify its content. Then we crafted this updated config file by putting numerous bytes into the field of the map file name in this updated config file. And as a result, the stack buffer overflow will be triggered during navigation map update. And besides, the service process has no stack canary protection, and the ASLR is not enabled in the Q1S operating system. So it's trivial to control the EIP register. And using the RP, we successfully exploit this stack buffer overflow and achieve the code execution in the HU Intel system with root privileges. And another attractive feature in NBT head unit is connective drive service. With the telematic communication box, the connective drive service can provide user with telematic and online functions, like real-time traffic information, online news, and online weather. And besides, in China, if you bought a new BMW car, it was free to use this service about 3 years. And after we reverse engineering the connected drive service, we found there's a provisioning profile, which is used to configure this service. And in this profile, it defines the backend URL of the online functions. And in this picture, it's a URL for the online news function. And it's using HTTPS, which seems to be secure. And by analyzing the traffic between the service and the backend server, we found that the service would send periodic requests to the backend server. And if the backend server responds some correct data, the service would try to download a new profile from the backend server to reconfigure the service. And in this picture, we can see that the service send a HTTP request to the backend server to download a new profile through the HTTP policy. And besides the new downloaded profile, it's just validated by MD5 algorithm. So obviously, this is really a security issue. If you could intercept the HTTP traffic, then you could hijack functions of the connected drive service. But in fact, in NBT head unit, connected drive service and provisioning update just works under the 3G and 2G networks. So in order to intercept the GPRS traffic, we need to use USRP and OpenBTS to set up a fake GSM base station. And once we force the telematic communication to connect to our fake GSM base station, then we can remotely trigger the provisioning update and deploy a new modified profile to the service. And in this modified profile, the online news URL has been changed from HTTPS to HTTP, so that we can do a man-in-the-middle attack against the online news function. And actually, the online news function in NBT head unit is processed by an in-car browser in the system, which is called the diff control browser. And for security purpose, the diff control browser is running as a low privileged browser user in the system, which is UID is 8. And since we have modified the online news URL with HTTP, so that we can manipulate HTTP traffic in our fake-based station. And according to the browser user agent, we knew that the different control browser is based on a WebKit engine. And we also found a corresponding WebKit library in the system, which is customized by Harman for QNS operating system. And this WebKit library was really out of date, and it had many public and exploitable vulnerabilities. And finally, we exploited this diff control browser by use of the free vulnerability in the sort function of just array object in the WebKit engine. Actually, it was the same vulnerabilities. It was the same vulnerability we used to exploit the Tesla in-car browser in the year 2016. And basically, two of the exploitations are similar, but in this case, here are some points that should be noted. In the diff control browser, all the JavaScript objects are allocated on the QNS system heap memory. So we need some knowledge about the QNS heap memory management. And in the diff control browser, there's no JIT. So there's also no writable buffer for the shellcode execution. And in order to achieve the code execution, we modified the function pointer of str2l in the GOT segment with the system function address. And then invoke the JavaScript data function to trigger the system function internally. And for more exploitation details, you can check out our white paper, which will be released on the Black Hat website. As mentioned before, the diff control browser is running as the browser user. So let it just allow us get a low privilege browser shell. But the diff control browser has no browser sandbox protection, and it has the ability to access the TCP network. So we can leverage the talk to risk condition vulnerability in the diagnosis service to get the root privileges from this browser shell. And after we got root access on the HU Intel system, the next step is how to send arbitrary CAN messages onto the KCAN bus. Because HU Intel and the HU Jacinto system are in the same QNet. And luckily, we found there's no password protection in the QNet network, so we can directly log into HU Intel system with root privileges. And the HU Intel system is responsible for CAN bus communication with the central gateway. So then we reverse engineering the corresponding CAN bus driver, and we found this CAN transmit function, which is used to send the log CAN messages. So in the end, we hooked this CAN transmit function to send the CAN messages with arbitrary CAN ID and arbitrary CAN data onto the KCAN bus. So in next part, Wenkai will introduce how to remotely exploit the telematic communication box.
Okay. Actually, this part should be is supposed to be finished talked by one of another college. He's Aohui Wang, but he cannot come here for some visa problem. So I will talk this section instead of him. And actually, TCP, the exploit of the TCP is a very important part in our exploitation. It helps us to finally make a remote attack. Let's talk about some of the details of the TCP. And there's two parts in the TCP. The first part is from Qualcomm's Rex RTOS, and the next part is an AutoSAR OS that's MCU to communication with the CAN bus. And when we try to reverse the RTOS, we find that there's a lot of tasks in the TCP, in the rack OS. So we mainly focus on such kinds of tasks. The first of all is about the NGTP. It's the BMW developed protocol. It's a very important part. And another thing is the SMS client, and also remote service and the last day call. And also there's a provisioning update. And all the details I will talk about later. First of all, the NGTP. When we try to reverse, we find that because BMW car has a remote services, you can use it to unlock the door and do something else. So, and also you can trigger the provisioning update. It's like to update the configuration in the TCB. And so, after we released our white paper, then we find there's a team from by the ADAC. They have also a SolidWorks about the NGTP. But the difference is at that time they had to they find a problem that the BMW used the HTTP, but at this time we had to face HTTPS. We had to find something to bypass the HTTPS protection. First of all, we should recover the NGTP messages. It's use ASN1 encoding, and also it's encrypted. But fortunately, we find that there's hard-coded encryption keys. So we can use this and by a lot of reverse, and that's finished by Aohui Wang. That's very cool. And finally, we can decode the messages. And when you try to snipe the messages to the TCB, then we can decode it, and also we can encode it. And that's the normal trigger process of the NGTP use. First of all, when the car is shut down and only the TCB is awake, so when you try to use the app to like unlock the door, first of all, it will send a message to the TCB and tell the TCB, let's wake the car. And then the TCB will make a HTTPS connection to the server, and they will transfer another NGTP messages, and for example, to do the unlock the door and something else. So in this in this picture, we can see there's it seems there's no problem, because the communication is protected by the HTTPS. But we think we find that BMW used the NGTP to trigger the remote services, also to wake the car. What about we send another message with another kinds of NGTP message to let the car unlock the door? And we successed. We find that the SMS and there's no protection. So first of all, you use the SMS to tell the car, let's wake up, and then tell the car, let's unlock the door. Then all the thing has worked. At this time, we can use the SMS to let the car unlock and do something else. And also in the NGTP, there are some key points. The first of all is about the VIN code. You should know the VIN code of the car. And also you should build a fake GSM base station. And at this time, use NGTP, you can only unlock door climate control, and you cannot do something else. And then it's about the provisioning update. It's like a configuration update. In this part, actually this configuration file is protected by the sign and protected by a lot of things. There's enough check. But finally, we found when to check the signature, there's a buffer overflow. By using this buffer overflow, finally we can make the code execution in the TCB, in the RTOS. But as I mentioned above, the first part of the TCB is the rack OS, and then there's a MCU, and then finally that's the CAN. So if you can compromise the rack OS, you can compromise the RTOS, you cannot send any message to the CAN. So you should still find some way to bypass the MCU to let it send a message. But we find another way. Because there's another function called the last state call. It's like some kinds of UDS diagnostic remotely to the car. So, and there's a configuration file in the TCB, in the rack OS. You can see there's some in-depth file, define the UDS messages and something else. And the MCU will help the rack OS to send the UDS message to the CAN. So at this time, now we can control now we can let the TCB send any UDS message we want. And how to make the final exploit, I will talk about later. And at this time, we just use the last state call to let the TCP send the UDS message. And then about how to attack the ECUs behind the gateway. You can see, we can go back to see the architecture of the car. There's domain isolation. If you can compromise the head unit, compromise the TCP I mentioned above, you cannot influence the whole car. You can only influence the ECUs on the maybe the KCAN4, it's the information domain. And there's less ECU on the information domain. Let's see some details because there's less ECUs on the infotainment domain, and also you cannot make too many effect or some influence to the car just by sending any message on the KCAN4. So we try to find something to break the domain isolation. And we got our focus on two functions. First of all is the diagnostic function from the OBD side. And another function is it's in the TCP, we call last state call. First of all, let's check something of the diagnostic function from the OBD side. First of all, one byte in the CAN ID, that means the source ECU ID. And also, there's the first byte of the CAN data at the target ECU ID. If we just use some sniping and when we try to do the diagnostic to the car, actually you can, if you have tried to modify your BMW car or something else, you can download some diagnostic software from online. And we just try to snipe the CAN messages, and we find that this kinds of format of the diagnostic package. For example, the normal diagnostic scheme is like 6F5. F5 means the tester from the OBD side. And 6.1 means that's the ID of the TCP. But when we try to reverse the IDs and reverse the direction of the CAN, we send the CAN message through the KCAN4. And also we will reverse the ID. For example, we just say our source ID is 6.1, that's the T box, and also the target ID is F5, that's the OBD side. Then, very interesting, we found that the gateway can transfer the message through the OBD side. It can also transfer the message through another CAN, and include the KCAN, that's the infotainment domain. At this moment, you can see the picture. That's the picture of the ESIS. That's the diagnostic software from BMW, and you can get the ECU ID through that software. And now everything seems to work. We can use this function to let the gateway help to transfer the messages through the infotainment domain. But we can only send this message through the head unit. As I mentioned above, that we should finish the remote attack. The remote attack we should start from the TCP. And TCP you cannot send any messages. So we put our focus on another kind of function in the TCP. Its name is last state call. And actually, the last state call is used routing control function in the BDC. It's very similar to the OBD diagnostic format. It's used that routing control function to help to let the gateway to send the messages to the other CAN, to transfer the message. So let's talk. So at this time, we just modified the UDS configuration files in the TCP, and the TCP will help to send the message we construct. And also, the gateway will help to use the last state call function to send the message to the other CANs. At this time, we can finally get code execution in the TCP and also code execution in the NBT and the head unit. And then we can let them send the UDS messages and let the gateway help to transfer the UDS messages. First of all, is now we can see at some of at some of time, we can let the cybersecurity to the functional safety, because you can see that's a very normal UDS diagnostic messages. When you try to combine them together, you can influence the car. Actually, there's another diagnostic software you can download online. And, there's a lot of diagnostic function you can find in the software, and there's a lot of things you can just diagnose the whole car, and you just get the message by snap to the can, and you can get different kinds of UDS messages. Then, for example, I just give you some example, and you can combine together. For example, you can use the reset ECUs. Also, you can try to change the driver's seat position, and something else. You can just combine the UDS together and lead the cybersecurity problem to finally the functional problem. So, in conclusion, we can route the head unit through the USB side and OBD side, and also fake GSM base station. Then we can route the head unit, and also we can trigger the normal function of the BMW remote reverse service used by some problem in the NGTP of SMS. Then we also find a bug to finally finish the code execution in the TCP. And then we can send any CAN messages or UDS messages through the MBT, the head unit, or the TCP to the KCAN buses, the KCAN4, and then use the function which is implemented in the gateway to help to transfer the UDS message to the other CANs, to the other ECUs, and finally we can influence the other ECUs to finish our final attack. And then will be a very interesting topic that's from BMW side, and they will talk about how the response to our report after they receive the report, and how they fix some of the problem in detail, and that's very interesting. Thanks.
So 1.5 years ago, I wanted to be on a skiing trip with friends. Actually, where I was the hospital. I was in hospital together with my wife, who had just given birth to my son. That was when I received a text message from my boss. And my boss wrote, "Hendrik, we received a report from KeenLab, and I knew this was going to be interesting." However, I would never have imagined to end up here on stage with you guys. So, as you have seen, KeenLab spent a tremendous amount of research on BMW cars between 2017 and 2018. Now, I want to give you a little insight on what we did at BMW. So, we received the report from KeenLab in February 2018. We have immediately dived into the vulnerabilities to confirm the vulnerabilities on the different modules. And we have then started to develop countermeasures, mitigations, and bug fixes for our cars. We have confirmed them on a test fleet and have then rolled it out to the whole BMW fleet in summer 2018. So what happens there? Basically, first of all, you need security experts. You need security experts to validate and analyze the results. So hackers like you and me. Then you need experts for the different functions that are affected. In this case, connected drive. You need experts for the car side, and you need experts for the backend side. And what you can see here at that picture is actually one of our cars inside an EMC hole. EMC is basically for conformance testing. That's a Faraday cage. So we set up our rogue base station in that cage of the colleagues that we asked for permission there. Because, of course, you don't want to have a rogue GSM base station out in the wild. Then we took our local development centers into the project, because you have different configurations and you have different infrastructure depending on the region and the world where the car is operated. We have different connected drive hubs there, and we do have different mobile service operators, for example, for the cars. And then, of course, we had to take our suppliers into the project, the suppliers of the head unit devices, of the navigation devices, suppliers of the telematics devices, and also the suppliers of the gateway modules. And that for all the generations that we had assessed and that were affected here. Last but not least, corporate quality. So basically our contact to the dealerships around the world. So we notified them about the bug fixes and patches and how to roll that out to the vehicles for those that needed physical contact to the vehicle. So let me go into a little more detail here. I already mentioned the report that we received from Keen Security Lab. That was really outstanding work. So that was very detailed. We received proof of concept, so it was great to work with that. And Keen Security Lab, you know, they're white hat hackers, so they had 4 white cars here, and they gave us results on that. So we boiled that basically down to 2 different generations that we had to look at in the navigation systems and the telematics units. But then, if you think of how many cars we built and how many cars we developed, what do you think? How many similar build-to-order cars out of the 2 million cars we produce in a year would there be? Basically, not even a handful. So we had many cars and many different configurations that we wanted to look at. Different options for different configurations, different regional configurations, different generations of control units, and different combinations of those control units. And that's how we dived into it. So to give you one example, you have seen the buffer overflow in the provisioning of connected drive, right? So that was one telematics unit that was affected with this bug, and that was limited to actually one of the connected drive hubs, in this case in China, where we had an additional misconfiguration. So we had an HTTP URL instead of the HTTPS URL inside. So in that case, it was exploitable. How did we address that? We addressed that with an over-the-air reconfiguration. So we moved from HTTP to HTTPS by contacting the cars and giving them a new configuration. So we reached all of the cars, in 86% of the cars in the first attempt. And then we tried again for a couple of times. And after the first retry, after the 4th retry, we had a success rate of 96%. So the rest, the 4%, are basically cars that are not connected anymore. For example, they're salvaged.
As Hendrik mentioned before, he got the text message when he was in the hospital with his wife and his newborn. So we had to find somebody else to get onto this topic quickly. As I had still his skis in my office, which he had left there when he had to run to the hospital, I also took over the responsibility for the incident response project, which actually became one of the most interesting ones I've done within BMW so far. But there was another reason for me to take over the responsibility for this project, because I had been part of the team that developed the connected drive and telematics functions in the control units we are actually talking about today. So I have the deep knowledge about the hows and whys to come up with the right countermeasures. So let's get into those. I will show you now in detail one of the countermeasures that we developed and rolled out. I'm using the attack against the remote door unlock as shown by Keen Security Lab just a couple of minutes before. To get into this, we will have a look at the flow again. But for us, the most important question was, how do we come up with a countermeasure that we can roll out as quickly as possible? Best of all, to roll it out over the air, so our customers get the improvement as quickly as possible without any activity on their side. So when we look at the remote service flow, the customer has a smartphone with a BMW connected app on it. When he executes the service, it sends a command to our backend server. The server then sends the SMS to our cars to wake it up with the NGTP protocol. After that, the flow is designed in a way that it's doing an HTTPS request to the backend to ask for the actual command to be executed. Yeah, all of those messages are NGTP messages. And then an important part comes. The car is checking then the already mentioned provisioning file. Within this provisioning file, there are not only technical parameters telling which URL to contact, but also it tells which services the customer has subscribed to. So in this case, the customer has subscribed to the services remote door unlock. So the car checks the provisioning, says it's okay. It will unlock the door and sends a command back to the BMW server. The customer gets a notification on his smartphone and knows everything worked fine. So how then does the attack work? So they set up a road base station, trap the car into their own 2G network, sends the wake-up SMS, which they're capable of doing so because they reverse engineered the protocol and they also extracted the pre-shared key with were part of the software. And then instead of having the car pulling the command via HTTPS, now they send the same message again. Unfortunately, one of our configurations inside the field accepted this SMS. Not all of the configurations did. It checks the provisioning and executes the service. So we thought, how can we come up with a countermeasure to prevent this? And provisioning was already mentioned before. We are also capable of providing new configurations to our car while they are in operation. So we said, let's just reconfigure our cars outside the affected ones to turn the service off via provisioning. So we did that with all the fleet. So what happens now when the attacker is coming? They send the SMS again, but the car is validating those against the configuration inside, saying, okay, the service is not allowed to run, and so the attack doesn't work any longer. But it has a drawback. The customer still wants to use the service, so we have to find a way of enabling it for him. What do we come up? We changed our configuration flow within our connected drive backend without any changes within the car. So when the customer is now executing the service, instead of directly sending the SMS to wake it up, we send another command to download a new configuration temporarily. This comes also to the car via SMS, and then it's fetching this configuration via the HTTPS connection. But in this case, this is only possible via HTTPS, not via SMS, because the payload is so much bigger. So then temporarily, the service is turned on inside the car. We then operate the normal remote execute path we did before. So it's coming down the message, checking provisioning, executing the service, sending the command back. And then we clean up, so to speak. So we set the car back to the secure configuration by reprovisioning it once again and turning all the services off again so the attack won't work any longer.
So just to give you an idea on what we do for security, we don't only address this internally, so we have teams of hackers, penetration testing, incident management, but also everywhere in the development. But also we have a website that you can report security research to. So if you go to our website, bmwgroup.com, you go to contact, and then you go to security, you will find an email address and you will find a PGP key that you can use to encrypt. So you can address your security research on the car, but also on corporate IT issues to this email address. And we're also very active in other parts. So for example, we brought the secure onboard communication protocol into AutoSAR. And we're active in AutoISAC, which is basically an association with the OEMs and the tier ones, where we discuss vulnerabilities to learn from them. Then there's ISO and SAE, who just develop a standard on how to bring security into the engineering process for embedded automotive. So, what are the key takeaways for you today? First of all, automotive is a very, very complex business. You have seen the different configurations, the different regional configurations even. different options, different regional configurations. You have seen the different life cycles, the long life cycle of the product. Then you've seen over-the-air updates are essential. This is vital to address security in a very, very fast manner. Then the automotive industry is changing. And this is not only the OEMs, the manufacturers, but also the suppliers. This has to go through the whole supply chain. And security is becoming an essential part in development and then also in operations. So when the car is on the road. And then as a last point, responsible disclosure is the key also in the automotive world to make the product more secure. And we want to thank you for being responsible and disclosing that to us so that we could be on stage here together. Thank you.